Hello, and thank you for having us. We are presenting our paper, Taming the Length Field on Binary Data, Calc languages. At first, we'll have a look at data serialization languages in general, and then how to properly specify them as Calc expressions, and then how to parse them efficiently with Calc finite state machines. In the end, we'll have some final remarks. So in general, there are three approaches to dealing with blobs of unknown length. The first one is end postfix notation, which is like brackets or quotation marks. Length prefix notation, which we'll focus on in our paper. And there you write the number of bytes in front of each segment. And count prefix notation, which is similar to length prefix notation, but you don't write the number of bytes, but the number of items of a given type. To get a little motivation, you probably know about Heartbleed, but you have the Heartbleed package, and it consists of the type field, length field n, an n-bit challenge, and some padding. And if I wanted to exploit it, if it's not properly implemented, I could just state a much higher number in the length field than the actual length of the challenge. And then the receiver would send me some arbitrary stuff from his memory, because he allocates the memory without actually checking how big the challenge is. This, of course, only happens if the implementation is not proper, which takes us to the core of the problem. We have two computers communicating with each other, and but we still have human error in it. So going on, we'll have net strings as our example language. A simple net string has a length field. Then is separated by a colon, then the n character string, and is finished with a comma. And there are also nested net strings, where you have outer length field m for the whole message, and then length fields for all the sub sequences and the strings and so on. So a good Heartbeat net string would look like 17 colon 7 colon payload comma padding comma, and if I wanted to exploit it, I would send just a really big number, and the other party would send me their secrets back. And we try to classify those net strings or length prefix languages in general into the Chomsky hierarchy, which has 4 classes of formal languages, and the classes higher in the table are supersets of the classes below. We have recursively enumerable, context-sensitive, context-free, and regular languages, but only context-free and regular languages are of practical use, since the other ones can't be parsed in reasonable time. The bad news is net strings and length prefix languages are context sensitive. We can prove this with the pumping lemma, which is a powerful tool of formal language theory, and I'll give you a short sketch. If you are not as familiar with it, it will not be formally correct or anything, just for the idea. So we split our string in 5 segments, x, u, y, v, and z, and then we pump it up by more instances of u and v, and all words given up from a specified length have to also be words of the language. And there are several cases here, but if u and v are both on the left-hand side or on the right-hand side, then it's of course trivial. The interesting case is if U is in the left-hand side and V is in the right-hand side. What happens if we do that? So if we add a symbol on the left side, we increase the number by factor 10. But of course, we only add a fixed number of symbols on the right-hand side. So if we would only add one symbol, then it would grow much slower than the left-hand side. Of course, we could say if we add a 0, then we do 10 on the left, but how long the V is a fixed number, so it would only work for 0 and not for all the other numbers. So this means net strings are context sensitive, which would mean that we probably shouldn't use them for any practical uses since we can't parse them efficiently. But the exponential parse time of context-sensitive languages is only worst case. There are subsets of context-sensitive languages, such as regular languages and context-free languages, which can be parsed efficiently. So maybe there is a subset of another subset of context-sensitive languages which contains length prefix languages, but can also be parsed in reasonable time. Therefore, we had to recall our knowledge of regular expressions and finite state machines. And then we enhanced this knowledge so they could handle length fields.
Yeah, so now we can take a closer look to our actual research. But yeah, at first, another recall of regular expressions. So yeah, regular languages can also be represented by regular expressions. So here, for example, the expression for a naive net string, which doesn't take the relation between the length prefix and the letters into account. Yeah, and this could be the final state machine for this expression. So yeah, final state machines in general can decide whether an input is a word of a certain language or expression or not. So here we are first in the initial state, number 1, and as long as we're reading digits, we stay there. And when the colon is read, we change to number 2, where we can read all the letters, and at the end, when we read the comma, we go to the final state and accept the word. So there are 2 different kinds of final state machines, deterministic and non-deterministic. And FSM is deterministic if there is at most one possible transition to take at a time for one symbol. If there are more than one, it is non-deterministic. So our example would be deterministic if the set of the letters doesn't contain the comma, but if it does, it would be non-deterministic. So yeah, but non-determinism and determinism are in this case equivalent, so we can transform non-determinism to determinism easily. Yeah, okay, now Calc regular expressions. So we saw the naive net string as an irregular expression, and now a proper net string as a Calc regular expression. And yeah, it looks like digit, superscript star, colon, dot decimal, and letter hash decimal, comma. So decimal is a function. For example, if you want to parse 11 colon hello world comma, 11 colon would be accepted by digit star colon and then evaluated by the function decimal to the number 11. And hello world is an exactly 11 byte long string, which then is accepted by the sub-expression letter hash decimal, and the final comma terminates the string. Okay, So yeah, Calc regular expressions are just an enhancement of regular expressions, although we have to predefine a function which takes an input out of sigma star and evaluates it to a natural number. And then we have a sub-expression r dot f, where r is a regular expression, so it could be also Calc regular, but nesting in this case is very complex and would take too much time to explain all the details around it. So yeah, assume it's a regular expression, then this sub-expression accepts every word that is part of R, of the language of R, and computes the value of the word of it out of the function f. Yeah. So the sub-expression t hash f, where t is also a regular expression, accepts all the words out of t that are f bytes long. So f was pre-evaluated. And t superscript f accepts then exactly f words of t. So another thing is they always have to become in pairs. So we have an evaluating part and a counting part. So r dot f, something in between, which also can be a Calc regular expression. Then t hash f is used for length prefix notation, and r dot f, something in between. T superscript f is used for for count prefix notation. So yeah, Calc regular languages and expressions are based on regular expressions. So in fact, regular expressions are a subclass of them. We only have to make one restriction, that Calc regular expressions always have to be prefix-free. And to be more specified, every sub-expression, like R and T, have to be prefix-free on their own. Yeah, note that established formal language assumes the parser to know the end of its input. And if we make this knowledge explicit, by reading a reserved end token, any language becomes prefix-free. So digit star isn't prefix-free, but with an added colon after it, it becomes prefix-free. So yeah, now to parse those expressions, we need some theoretic machines, and we call them Calc finite state machines or Calc FSMs. As a short recall, this is the FSM for a naive net string. And a Calc FSM for the proper net string could look like this. We added an accumulator, and the statements for the accumulator are here highlighted in blue. So as long as we're reading digit as an input, we store these digits in the accumulator with the store function. And then when we read the expected colon, we evaluated the input in the accumulator to a natural number. And then when we read all the letters, we decrement it for every letter by 1 until it is hopefully 0. And when the comma, which terminates the string, comes in the input, we check the accumulator if it is really 0, and only if it is, we can go to the accepting state and accept the word. So, for example, I will show you how it works for the string 5 colon hello world comma. So, the first symbol we read is 5, and we put it in the accumulator, and then when the colon comes, we evaluate it, and the symbol 5 is evaluated to the number 5, and then we read the h, and decrement the accumulator by 1, which is now the value of 4. Same we do for E, for L, for the second L and the O. And then the next symbol we read is the comma. So we check if our accumulator is really 0, and it is, so we can accept the string, which is a proper net string, as you see. So we try to minimize the changes from FSMs to Calc FSMs, as we tried it also with the regular and Calc regular expressions. So they're not very strong, but strong enough to pass the most length prefix languages. And yeah, a little more detail to the accumulator. It has two states where it can be in. So first, at the beginning, it is in string state, where it can be called the store function. And after it is evaluated, it changes to numeric state, where we can decrement it by 1. And afterwards, compare it if it is 0 or not. So we can only accept an input if all accumulators of an FSM are 0 and we're in an accepting state, so similar to FSMs. If one of this is not the case, we cannot accept. But also, if our accumulator is 0 and a transition with a decrementing statement is called, we reject the input as well. So in our research, it turned out that there's 3 different kinds of Calc FSMs. So we have here type 1, which is the non-deterministic one, and type 2, which is the deterministic. The example for the net strings is deterministic. So yeah, and we have a third type, kind of a meta type, which where we write just a Calc regular expression on one transition. So yeah, here you can see the relations between the 3 different types. Type 3 is equivalent to the set of Calc regular languages and can be transformed into a type 2 with an algorithm. But type 1 and type 2 are here not equivalent like in the regular FSMs. Type 1 is too strong for just regular expressions. So yeah, in the end, if we can describe a length prefix language with a Calc regular expression, we can also transform it to a deterministic Calc FSM and parse it in less than exponential time.
Okay, some final remarks. In addition, we introduced a kind of extended Backus-Nauer form like meta-language, which has some commonly used expressions from regular expressions like ranges and brackets and Kleene stars and such on for human readability and parser generation. And then I'll wrap things up. So length prefix languages are commonly used in data serialization, but we are not really equipped with the tools to properly specify them and parse them efficiently. And therefore we introduced Calc regular languages, which, even though they are context sensitive, can be parsed in reasonable time. And this is a starting step for future research. We would have to study more properties of those Calc regular languages and write our own parser generator for them, and maybe we could even introduce a thing like deterministic Calc context-free languages, which would allow us a good amount of nesting. Yeah. That's it from us. Any questions? Yes?
Seems like a good idea. It also seems like you could generalize it so that the function f, which instead of just computing a number, could produce, in other contexts, some arbitrary function that would be then incremented as it went, applied to the data as you go through the later loop. So you might say something like, I want a string, but no more than 3 E's can appear. And then as you went around the loop, instead of subtracting 1, you've only subtracted 1 on the E's, that type of thing.
Yeah, that's more or less the idea. So it's not this fixed function, but you could introduce any function you want, and it will somehow calculate a value from the string you passed, and then you decrement it.
You just do decrement one, you just have a different transition for the E from the other letters.
Well, yeah, I guess what I'm just saying is the general idea is you read something, that gives you a function, and then that function is applied on.
That's what they describe.
Yeah, he was talking about specific numbers.
So if I may intervene, my obvious next question would be, this is great. I mean, no more heartbleed, right? At least not committed blindly. But what about parser equivalence? Let's say we have two of these automata. Are we in a situation when we can prove equivalence, or
Of two. Calc.
of two automata that accept two Calc regular languages? And then can we say if they, can we algorithmically say if they accept the same language or not?
Yeah, I think, I'm not sure if it is in the paper or we did it afterwards, but it's similar to the proof or the regular languages and their machines. We did it for our.
Okay,
I'm not
great.
sure
This
if it
is,
is in
this
the
is
paper
even-
yet, but we did it. So.
This is even better news, right?
We used some kind of table filling algorithm, like for regular languages, but we extended it a little. Yeah.
Great. Any more questions?
I didn't catch it. Sorry, is it possible in your calculator language expressions to nest these length fields so that you have internal structures which themselves have these length values?
Yeah, I just skipped nesting because it sometimes gets very complex.
That was the complex net strings though, right? Like net
Yeah.
strings,
Yeah.
net strings
Also,
embedded.
we-
Yeah, it's in some expressions when you nest them, it gets really complex and cause some trouble in some cases. But so
Yeah, we looked into
it
it
is
and we
possible.
tried to do some proofs, but it's not as thought out as that we could use it already.
Okay, yeah, because I was thinking about the fact that when you do that, you have to make your protocol cognizant of the fact that the nesting is happening, and then also you need to check that at the end of the outer field, the inner fields are also equally exhausted, or you get kind of an interleaved structure that wouldn't probably have any of the properties that you said. But that would be interesting to see future work in that.